So let's skip this. Now we're here. After we combine the half reactions here, we make sure the atoms balance. So 1 nitrogen, 3 oxygens. 2 plus 1 is 3 oxygens, 4 hydrogens. 2 times 2 is 4 hydrogens, 3 silvers, 3 silvers. Not only must the atoms balance, but the charges must balance too. And I'm talking about the net charge, not the individual charges on the atoms, but the net charge. So this is minus, this is plus 4. So minus 1 plus 4 is plus 3. These are 0. So I got plus 3 total net charge on the left. And then I have 3 times plus 1, which gives me a plus 3. This is 0, this is 0. So plus 3 charge on the left, net, plus 3 charge on the right, net. So the charges are balanced. So if the atoms balance and the charges balance, then this equation is correct. Now this is the net ionic equation. You know, once we get rid of all the spectators, this would be the net ionic. And so for the chart method, one thing we don't get is we don't get the CE, we don't get the IE, we're just left with the NIE, which is okay. We can just deal with the NIE. Did you get a driving force for this? Have you gotten there yet or not yet? All right, let's assign these. So nitrate and H+, this is our oxidizer. Ag is our, what about Ag+? Well, let's just assign its role first. This is why I do it off these half reactions. Off the half reactions it's easy because of conjugate pairs. If this is our reducer, then Ag+ must be our conjugate oxidizer. If nitrate and H+ is our oxidizer, then NO and water must be our conjugate reducer. And so I'd like to assign it off the half reactions because it's easier. And so the Ag+ is our oxidizer going backwards, if we're to go backwards. And NO and water will be our reducer going backwards. Then you just use the chart. Did you get driving force for this? Or take a look at the chart now. Are we going to get driving force for this? Stronger to weaker. Just looking at the rankings of oxidizer and the rankings for reducer, we have driving force. It's stronger to weaker. And so in single replacement, you really do no redox reaction, but indeed a redox reaction actually occurs. A redox reaction occurs, we figured out by the chart. And so, which brings us to this. The single replacement, the advantage of single replacement is that it's simple pattern, it's pretty easy to predict, and if you're never asked for one of the exceptions, it's fine to use. The disadvantage is if you're asked for one of the exceptions, then it doesn't work. And therefore we need an alternate method. The chart method works for everything, as long as it's on the chart. I shouldn't say it works for everything because, you know, even the chart method, there's things that could potentially throw you off, but it's a much more reliable method. And so rather than using the single replacement, you could use all these, A plus Bx, using the chart method, but after you do a bunch of these and you see what the exceptions are, then you'll better recognize it. So I use a combination of methods. I use both the single replacement and the chart method. For example, if I look at the single replacement and I see that's not one of the exceptions, and that's much faster, you can do it quickly rather than using the chart. But what are the exceptions? That's what you have to drill down. And so the thing I don't like is the single replacement is kind of the shortcut method. And so it's like learning the shortcuts before you learn the full. You know. full method. All right, there are some other shortcuts that we can learn as well. And so let's take a look at some of these. Like, for example, I think I asked you near the beginning, what are the chemical properties? Did I ask you this? And so let's just sum it up for chemical reactions now. There are more redox, which we'll talk about a little bit later. You know, I should say that there are some risks, you know, with even using the chart, because not everything's on the chart. That's a problem. And so, like, for example, the chart method is much more reliable. However, what happens if there's something that's not on the chart? So let's do this. I'm going to take some potassium permanganate. And some hydrochloric acid. And some ethanol. Will anything happen there? Now, the situation is this. Ethanol is not on the chart. But ethanol is pretty reactive. And that's something that you just know from memorized knowledge. What do you know about ethanol? Ethanol is like the alcohol they use in alcoholic beverages. But do you know anything else about ethanol? Well, one thing that a lot of people know about alcohols is alcohols typically are pretty flammable. And so if ethanol is pretty flammable, what does that mean? Like, would you say ethanol is even more flammable than iron? Is ethanol easier to burn than iron? Yeah, I'd probably say so. Is ethanol easier to burn than magnesium? Did you see when I ignited the magnesium in lab? Remember the bright white light? Magnesium is pretty flammable. Maybe not as flammable there. I'd place ethanol, maybe, do you think it's as flammable as sodium? Do you remember the sodium? At that lake in Washington, Lake Lenore, Washington? So I'd place ethanol probably around here in terms of, have you heard about the lithium batteries catching on fire? There's a lithium battery plant in Asia that completely burnt down because of that. And so ethanol, you would say, okay, ethanol's not on the chart, but I would say it's a pretty strong reducer. Like methane, you know, is methane on the chart? Methane's not on the chart, but that's also a pretty strong reducer. And so this is where I'm going to do one more for redox. This is called the skeleton reaction. Skeleton reaction. And so what makes methanol and other things burn, and whereas other carbon-containing compounds don't burn so well? So for example, CO2, you know, if I ran out of methane and I ran out of ethanol, could I use CO2 to make a fire? Does CO2 burn? But it's a carbon-containing compound. Ethanol is a carbon-containing compound. Aren't all carbon-containing compounds flammable? And so that has to do with one of the best and most flammable ones is methane. Methane's highly flammable. So when we're looking at redox properties for this, I know methane's flammable. In fact, did you hear about over the weekend about the explosion? This happened over the weekend. Where was it? Harrisburg, Pennsylvania? Or was it? No, it wasn't Harrisburg. This was a small one here. It was Durham, North Carolina. 2 women off the couch prompted grandma to jump from the roof. But fortunately, nobody died in this one, right? Harrisburg. Durham, North Carolina. This happened 5 days ago. It wasn't over the weekend. Get out of this. Yeah, this one killed. Killing one, injuring more than a dozen others. Methane is a powerful reducer. Powerful reducer, so it can produce violent reactions like that. Every year there's natural gas explosion. Because I've been tracking it, every year people die from natural gas explosions. So methane's kind of dangerous. What makes it so reactive? What makes it so dangerous? What about methane that makes it dangerous? So what we're going to do is we're going to try to correlate things. You know, what we want to do is stop this video here. Got this. So that means this is explosive, highly flammable. That means it's a good reducer. So what makes methane such a good reducer? I'm way over time. Sorry. Let's stop. I'll stop here. Let's take a break and then.